Okay, so we were applying the energy balance to the spin control volume, and we said that we have here the flux of conduction will be divided into radiation and convection fluxes. So by writing this, sorry, it's for the, we were doing this problem. So when doing this, okay, we can just put all fluxes in the equation. As we said, Q out is mainly divided into convection and radiation, and the heat processes that are taking place will be out through the lateral surface, and the lateral surface is pi dl. So this term is the convective flux H times pi dl times delta T. This is the radiation flux epsilon pi dl sigma T surface power 4 minus T surrounding power 4, while Q conduction, okay, is equal to the summation of these two. So this is Q conduction. And since they ask for the conduction per unit length, all we have to do is to divide this term by L. When we divide this term by L, we should also divide Q out by L. So L will cancel out, and then we will be able to calculate what is the heat loss per unit length of pipe, and this heat loss will be equal to the conduction per unit length at the surface. Okay. Now, another problem that is little bit related to the real life, okay, and it's very important to consider such issues, especially when we study the human body. So you know that humans are able to control their heat production rate and heat loss rate to maintain a nearly constant core temperature under a wide range of environmental conditions. This is what is called thermoregulation. So, from the perspective of calculating heat transfer between a human body and its surroundings, we need to focus on a layer of skin and fat with its outer surface exposed to the environment and its inner surface at a temperature slightly less than the core temperature. We'll consider in this case a person with a skin fat layer of thickness 3 millimeter and effective thermal conductivity of 0.3 watt per meter Kelvin. The person has a surface area A equals to 1.8 meters square and is dressed in a bathing suit. The emissivity of the skin is 0.95. So what we will do first, we want to find what is the convection heat transfer from the person to the environment. If we consider that first the person is in still air at T infinity equal to 297 Kelvin, and we will compare this after with the heat loss by if you have water. Okay, so first, if we consider air, because they gave us the temperature of air, and we have also the emissivity from the skin, we can assume that the walls of the bathroom are also at the same temperature of air, which is 297 Kelvin. And we can say then that the heat loss from the skin is through convection and radiation. Okay? So here the idea is that within the thin layer of skin fat layer, we have heat flux by conduction, Q conduction. And this heat will be transferred out of the skin layer by convection and radiation when you have air. Okay, but when you have water, as we said, water is opaque to radiation. This is why when you have water, you only have heat loss by convection and no more by radiation. So for the first question, you have air, so you consider both convection and radiation. And what you are interested in is to calculate the surface temperature of your skin. Okay, you want to find what is T surface. TS. Knowing that the air temperature is equal to 35 degrees. So first, T surface will figure out into the conduction rate and also in the convection and radiation rates. So we will be able to write an equation where the only unknown is T surface, and by solving this equation, we can get what is TS. So all we have to do is to express first the conduction, convection, and radiation function of the surface temperature. If we start with the conduction, we have that Q conduction is equal to K times the area of the skin layer times, we know that conduction will be from the highest temperature towards the lower temperature. So it's 35. But please pay attention for units, okay? Whenever you have radiation here, T to the power 4, you need to have all your temperatures in Kelvin. This is why I will use for the inner temperatures the Kelvin scale. So it's a 308 minus T surface over the thickness of my layer. So over thickness, okay? And this will be equal to Q convection plus Q radiation, which has the same expressions as we have seen before. HA delta T and epsilon sigma A T surface 4 minus T surrounding T walls to the power 4. Okay? So if you write this energy balance, you will get the following. You will get that, as we mentioned, QA delta T over L. So here we can add A, but A will cancel out because we'll have it also in the convective term and in the radiation term. So it will cancel out. We can drop it from the equation. And then we'll get an equation in which the only unknown is T surface. But here, this equation is not linear. It's not easy to solve. So we can solve it by trial and error, okay? Or we can solve it by iterative procedure. But in general, I will not ask you to solve it. All you have to do is to reach this equation, this stage. Okay, this is enough for me to reach this stage and say the only unknown in this equation is Ts, so we can solve for Ts. As I told you before, if you remember, sometimes we can linearize the radiation by including a coefficient HR in order to simplify the expression of the radiation term. And in this way, we can transform the equation to linear, and this will help into the solution, especially if you are using programming to solve for Ts. Now, in the second part, we want to find T surface, but in case we have water in contact with the skin layer. We know that water is characterized by a larger convection coefficient. So we can expect that whenever we have contact with water, the skin temperature will be smaller. But here, we should pay attention that whenever we have water contact, we don't have any more radiation because water will be opaque to radiation transfer. Okay, so if you want to write the equation in case you have contact with water, you should remove this term, but the convective coefficient will be larger. Okay, so you can expect lower surface temperatures. So if you calculate the heat loss, in case in the first case where you have air, the heat loss will be equal to 146 watts. Okay, while when we consider the water, the heat loss rate is much larger, despite the fact that you don't have radiation anymore. Okay, so this is why we say that convection by water is much larger than convection by air. And even if we don't have radiation, since the convective coefficient for water is much larger, the heat loss rate with water will be considerable. Okay, any question on this? And if you have any question related to the material and videos of chapter 2, I'm ready for any question. Okay, so we'll stop here for today. And as I told you, in case you want to ask me about the project, you can send me the outline anytime or ask for an online meeting. Okay? Bye-bye.